Hi, Henry here. A story I thought about for years, when ice covered the whole Earth for 50 million years. If you'd like more, subscribe. I think you'll like it. 700 million years ago, the Earth froze. Not the way you might imagine when you hear that phrase. This wasn't ice creeping down from the high latitudes while the tropics stay warm. The whole planet went under. From the equator to both poles, every ocean and every coastline buried beneath ice that in places ran more than a kilometer deep. There wasn't a square meter of liquid water at the surface. No open sea, no rivers, no rain. Whatever water vapor the cold atmosphere could still hold had long since fallen as snow and locked itself into the ice. Geologists call this the cryogenian period. It lasted, by most reckonings, around 50 million years. Some accounts stretch the number further. Nobody knows the exact duration, and the rock record gets harder to read the deeper into deep time you go. 50 million years. To put that in perspective, that's roughly 20 times longer than the human species has stood, and 10 times longer than primates have lived. The planet just wasn't the same world it had been before, not for a stretch of time so vast that ordinary human timescales don't quite reach it. In a desert in southern Africa, in what's now Namibia, the evidence of that frozen world still lies on the surface. It isn't buried, nor hidden. Wind and slow tectonic uplift have weathered the evidence into ridges along the skeleton coast, exposed by ages of slow weathering. Among those ridges sit fist-sized stones embedded in dark rock. They were carried, once, in glaciers across what was then a frozen ocean, and they fell into the soft seafloor mud when the ice melted just enough to release them. Geologists call them dropstones. Their presence in tropical latitude rock that sat at or near the equator deep in the cryogenian, stands among the strongest pieces of evidence we've got that the entire Earth, even its warmest belts, froze solid. What did it look like from above? From orbit, the planet would have shown as a single white pearl drifting through space. Silent, unbroken. The surface was so reflective that almost any sunlight reaching it bounced back into the dark, and the planet kept losing more heat than it gained, day after day, year after year. The ice didn't come to destroy life. It came to change it. What happened during those long ages remains among the strangest chapters in Earth's long history. How did the planet freeze in the first place? What survived underneath the ice? And what in time broke the freeze? These questions are part of an old debate, still unsettled in places. The chapter also turns out to matter quietly. Without it, the world that came after, the world of complex life and fossils that look like animals and oceans full of moving things, wouldn't have existed in the form it did. Tonight, the story of a planet that froze solid for 50 million years and what waited underneath the ice. To understand how a planet freezes, it helps to know what the planet looked like before the cold arrived. And the world, 750 million years back, was by most accounts a comfortable place. Continents were gathered into a single mass called Rodinia. It wasn't the Pangea that most people have heard of, that came later, much later, assembled and then broken apart in the time of the dinosaurs and the great coal forests. Rodinia was older. It formed around 1 billion years back when several smaller land masses collided and fused along mountain belts that have long since eroded to their roots. By that early cryogenian threshold, it was beginning to show its age. Cracks were forming. Rift valleys opened like slow wounds along its margins. But it was still, more or less, one continent, sitting mostly in the tropics. What were the oceans like? Warm, not uniformly. There were currents and temperature gradients, just as there are today, but the shallow seas along Rodinia's coastline would have felt pleasant. 25, perhaps 30 degrees Celsius in places. A water where you'd wade in without thinking about it. Life was simpler then. Not simple in the way that implies primitive. There is nothing primitive about an organism that has survived a billion-year stretch of change, but simpler in form. Oceans were dominated by bacteria. Cyanobacteria, mostly the same phylum that had produced oxygen for more than 1 billion years. They built stromatolites, layered mounds of mineral material held together by bacterial mats, rising from the shallow ocean floor in forms that look, to a geologist's eye, a little like stacked pancakes left in the rain. Modern stromatolites still survive in a few isolated places. Shark Bay in Australia, the Pilbara region. Their surfaces feel like rough concrete with a faint slickness, as though something alive had passed through recently and left an impression. In a sense, something had. Those mats were the engines of the Proterozoic world. They captured sunlight, water molecules were split, and oxygen was released as a waste product. They'd been doing it so long, and so steadily, that the atmosphere had changed around them. Oxygen levels were lower than today. Perhaps 10 to 15% of the modern value. Nobody knows the exact figure, yet it kept rising, slowly, the way everything rises in deep time. Given enough centuries, even a whisper of chemistry becomes a shout. But oxygen was only half the story. The other half was carbon dioxide. And this is where things get delicate. How faint was the sun back then? About 6% fainter than it is today. 6% sounds negligible, trivial even. It doesn't sound like much. Had you stood on that Rodinian coast and looked up, the sun would have appeared the same, bright, warm, the dominant light in a pale sky. Your eyes wouldn't have noticed the difference, but the physics would have. 6% less solar energy reaching the surface means, all else being equal, a colder planet, much colder. Cold enough, by some calculations, that the oceans should have frozen entirely, and yet they hadn't. The water was warm. Stromatolites were growing. Life was doing what life does, quietly and persistently, in the shallow seas around a tropical supercontinent. Carbon dioxide was the reason. Greenhouse gases, carbon dioxide, methane, water vapor, were present in the atmosphere at concentrations high enough to trap the extra heat that the weaker sun couldn't provide. It was a compensation, a balance. The sun gave less, and the air held more. What followed was a world that functioned. Not perfectly, not with enormous margin, yet it worked. I think about this balance more than I probably should. It's one of those things in geology that sounds simple when you first learn it, and then grows more unsettling the longer you sit with it. The planet was habitable not because conditions were naturally ideal, but because two independent variables, solar output and atmospheric makeup, happened to offset each other at just the right ratio. If the sun had been a little fainter, or the gas a little thinner, the balance would have tipped, and once it tipped, no easy way back. Earth chemists call it a thermostat, and I understand why, but I've always thought that was a generous figure. A thermostat implies control. It implies a mechanism that notices when things go wrong and corrects them. Earth's climate system in the late Neo-Proterozoic had nothing like that. What it had was feedback loops, processes that amplified change rather than damping it. When temperatures dropped, ice formed. White ice reflected sunlight. With that reflection, temperatures dropped further. The system didn't correct. It accelerated. Back at that early cryogenian threshold, none of that had happened yet. Feedbacks were dormant. Balance held. Oceans stayed warm. The stromatolites grew. The cyanobacteria broke water molecules apart and released their oxygen. The sun, 6% fainter, burning through its hydrogen, lit the whole evening in a softer amber than the modern Namibian dusk that now covers these old ridges. Warmth was real, but it was borrowed, and the debt was about to come due. There's a phrase I've heard other geologists use when they're talking about the Neoproterozoic climate: metastable. It means the system was stable, but only within a narrow band of conditions. Push it gently, and it would return to balance. Lean against it hard enough, and it would fall off a cliff. That greenhouse balance, the kind that holds until it doesn't, kept 3/4 of a billion years ago warm and wet. Were the conditions slightly different, the story I'm about to tell might never have happened. Oceans might have cooled, a degree or two, recovered, carried on. Rodinia might have drifted, broken apart, reassembled. The planet would have aged without incident. But the conditions weren't slightly different. They were precisely wrong. And the thing that pushed the climate off its narrow ledge was, of all things, the continent itself. Rodinia was beginning to break. A continent doesn't break quietly, or rather, it does on a human timescale. There's nothing to hear. But the consequences are not quiet at all. Rodinia began to rift sometime around 800 million years back. The process was familiar, at least in geological terms. Hot material rising from the mantle pressed against the base of the continental crust, thinning it, cracking it, pulling it apart. Rift valleys formed, long narrow basins that filled with sediment and water. Volcanic eruptions accompanied the stretching, pouring basalt onto the valley floors. Slowly, over a long age, the rifts widened into seaways, the seaways into oceans. Rodinia was splitting apart, and where one continent had been, several were forming. How often does this happen? Continents assemble and break apart on a cycle that runs roughly every 500 million years, give or take. It's one of the great rhythms of geology, slow, patient, unavoidable. And normally, when a continent rifts, the volcanic activity that accompanies the splitting releases carbon dioxide into the atmosphere. That carbon dioxide warms the planet. A warm planet weathers rock, which consumes carbon dioxide, which cools the planet, which reduces weathering, which lets carbon dioxide build up again. So a cycle forms, slow, self-regulating, the kind of cycle that has kept Earth's temperature within a livable range for most of its 4.5 billion year history. But Rodinia's breakup was different. Not in kind, the physics was the same, but in consequence. And the difference came down to geography. When Rodinia split, it created something the planet hadn't had in quite the same way before. Thousands of kilometers of fresh coastline, positioned in the tropics. New continental fragments sat in warm, wet latitudes where rainfall was heavy and temperatures were high. Along those new coastlines, freshly broken rock, silicate rock, basalt, granite, was exposed to the weather for the first time in ages. A rift valley in the modern world, the East African Rift, for instance, where the process is happening today, is a reasonable analogy for what Rodinia's interior was beginning to look like, though the scale was different. What's striking about fresh rift topography is the rawness of the rock. Raw basalt, no soil yet, cliff faces where the minerals remain crystalline, sharp-edged, chemically reactive. Rain hits that rock and something happens. Something quiet, the kind of thing that changes the world. What happens when rainwater meets fresh silicate rock? The chemistry is straightforward, though its consequences aren't. Rainwater is slightly acidic because it absorbs carbon dioxide from the atmosphere on its way down. When it meets silicate rock, a reaction occurs. Silicate minerals dissolve. Calcium and magnesium ions are released into the water. And in the process, carbon dioxide is consumed, pulled out of the atmosphere and locked into dissolved bicarbonate that eventually washes into the ocean and precipitates as carbonate rock on the seafloor. One raindrop, one grain of feldspar, a molecule of the gas removed from the air. It doesn't sound like much. And for any single reaction, it isn't. But Rodinia's breakup wasn't one reaction. It was a continent's worth of fresh silicate rock, exposed to tropical rainfall, across thousands of kilometers of coastline, across vast ages. The scale of the weathering was by any measure extraordinary. For every molecule of silicate that dissolved in rainwater, one molecule of carbon dioxide left the atmosphere, grain by grain, drop by drop. The planet was cooling itself. Diamictite, the broken glacier-carried rock embedded with dropstones, is the evidence of what came next. Geochemists use a phrase for this process, this silicate weathering thermostat. I keep coming back to that word, thermostat. Under normal circumstances, it's a stabilizing feedback. When the planet warms, weathering speeds up, more carbon dioxide is consumed, temperatures fall. As the planet cools, weathering slows, carbon dioxide accumulates, temperatures rise. The system corrects itself. It's one of the reasons Earth has remained habitable while Venus boiled and Mars froze, not because our planet is special, but because its surface chemistry happens to regulate its own atmosphere, slowly, over millions of years. But there's a flaw in the thermostat. It assumes that the rate of carbon dioxide release, from volcanoes, from mid-ocean ridges, from the slow chemical breath of the mantle, roughly matches the rate of carbon dioxide consumption through weathering. And for most of Earth's history, that assumption held. The input balanced the output. Books were even. Rodinia's breakup tipped the books. Too much fresh rock, excessive rain, a glut of tropical coastline consuming carbon dioxide faster than the volcanoes could replace it. The atmosphere's greenhouse buffer, the carbon dioxide blanket that had been balancing for the faint sun, was thinning. Not in a dramatic way, and not in a way that anyone, had anyone existed to notice, would have called a crisis. But centimeter by centimeter of weathered rock, molecule by molecule of consumed carbon dioxide, the safety margin was shrinking. Why did the margin shrink so quietly? Nobody can say with certainty. The reason isn't fully understood, only that the geometry of the new tropical coastlines amplified what had always been a slow, balanced process into something one-sided. In modern river gorges, this same process can still be observed happening in real time. Water runs slightly milky, dissolved minerals, calcium and silicate, carried downstream toward the ocean. Gentle, unhurried. The kind of process easy to overlook. Rain falls, rock dissolves, water carries the remains downstream. The whole thing takes place at the scale of individual mineral grains, and it's about as dramatic as watching paint dry. But multiply it by a long age in a continental surface area, and the numbers become something else entirely. Temperatures were dropping, a fraction of a degree per million years, perhaps less. A cooling so faint, it would be invisible in any human record, invisible even in most rock records. Still, it was there. Ocean kept notes. Isotope ratios in marine carbonates from this period show it. A slow, steady decline in the proportion of carbon-13, which geochemists interpret as a signal of decreasing life output and shifting atmospheric makeup. The ocean was recording what the atmosphere was losing. There was another factor, quieter still. As temperatures fell even slightly, ice began to form at the poles. Not much, seasonal ice, the kind that forms and melts in an annual rhythm. But ice is white. White surfaces reflect sunlight back into space instead of absorbing it as heat. Geoscientists call this the white bounce effect, and it's one of the most powerful feedback mechanisms in the climate system. A little more ice, more reflection, less heat soaked up, cooler temperatures, even more ice. The cycle was beginning. Not fast, nothing in deep time is fast, but it was beginning. And the planet With its faint sun and its thinning greenhouse, and its thousands of kilometers of freshly exposed silicate rock, drinking carbon dioxide from the atmosphere, grain by grain, drop by drop, was drifting toward a threshold it had never crossed before. Over these same ridges in Namibia, the rocks have watched countless evenings pass. They recorded the warmth, the weathering, the slow chemical theft of a planet's greenhouse blanket. And they recorded what came after. Balance was gone. What replaced it was ice. Sturtian glaciation began about 717 million years ago. I've read that number many times, and it has never once felt real. 717 million. It is a figure that sits flat on a page and refuses to breathe. And yet that's the moment the planet crossed a line it had been approaching across the long ages. The greenhouse was thin. Carbon dioxide that had kept the faint sun's warmth trapped against the surface, the borrowed warmth, the compensating blanket, had been drawn down, grain by the weathering of Rodinia's broken coastlines. With less CO2 aloft, the planet was cold enough finally for the ice to begin in earnest. It started at the poles. That part will sound unstriking. Ice has formed at the poles many times in Earth's long history, and in most cases it simply sits there, a white cap on the top and bottom of the world. The cap reflects some sunlight. It cools its local neighborhood, but what does that change? Almost nothing. Earth's overall condition stays the same. Polar ice, under ordinary circumstances, is a stable feature. The tropics stay warm. Mid-latitudes cycle between glacials and interglacials. Such a system accommodates. But these weren't ordinary circumstances. Carbon dioxide had run thin. The sun was too faint. Once the ice formed at the poles, it didn't stay at the poles. It crept outward. Slowly, perhaps a kilometer a year, perhaps less, the glaciers advanced from the high latitudes toward the temperate zones. Sea ice thickened along the polar margins of the oceans. The snow line, that altitude above which precipitation falls as snow rather than rain, dropped lower with each passing century. Mountain glaciers descended into valleys never reached before. Each new kilometer of ice did the same thing. Dark land and dark water turned white. The ground, once an absorber, became with each new sheet a bright mirror that bounced the dwindling sunlight back out into the dark. Modern glaciers in Norway, in Patagonia, in Greenland, share a quality that doesn't come through in photographs. They are aggressively bright. Not bright as a sunny day is bright, but bright in a way that makes the air feel different, because so much energy is being bounced away rather than absorbed. Temperature on a glacier isn't just lower because of the altitude or the latitude, it's lower because the surface itself is rejecting heat. Ice is, in a physical sense, refusing to warm up. What happens when albedo feedback operates at continental scale? The ice reflects sunlight, which cools the area, which makes more ice, which reflects more sunlight. That feedback was now running at the scale of continents. It was accelerating. Were the carbon dioxide in the air a little higher, the feedback might have slowed itself. Warmer air holds more water vapor, which is itself a greenhouse gas. That extra insulation can sometimes offset the cooling from additional ice. It's one of the self-correcting mechanisms that has prevented runaway glaciation during most of Earth's ice ages. The system wobbles, but it doesn't fall. Ice advances, but then it retreats. This time, there wasn't enough carbon dioxide left to generate the counterpush. The greenhouse had been stripped too thin by the weathering, and the faint sun couldn't compensate. Every new sheet of ice deepened the cooling. The weak sunlight reflected back into space, and the ice crept further from the poles. I find it strange that the quietest processes produce the most irreversible outcomes. Carbon dioxide drawdown that set this in motion was gentle. Weathering of rock by rain is, on a human time scale, one of the least dramatic events in chemistry. and the advance of ice from the poles toward the equator happened so slowly that, had any creature been capable of observing it, it might have been almost the same as the normal passage of seasons. A winter that lasted a little longer than the last. The next spring came a little later, a coastline where the ice used to melt by midsummer, and then one year it didn't. And then the next year, it didn't again. Ice crossed 60 degrees latitude, then 50, then 40. Coastlines that had been washed by temperate currents were sealed under white. Shallow seas where stromatolites had grown for ages went dark beneath the ice and stayed dark. The waves against a shore went silent, gradually, then completely, when water stops moving because it can't. There's a kind of silence the Arctic still produces today, not the absence of noise, the presence of stillness, a positive quality, as though the landscape has made a decision to hold its breath. Salt crystals form along the edges of freezing water. Fine and brittle at first. Once the temperature drops far enough, the crystals stop growing and the surface goes smooth. Last ripples freeze in place. The ocean becomes a floor. Still, the feedback continued. Geophysical models are clear on this point, and I have read several of them closely. Once ice reaches about 30 degrees latitude, roughly the latitude of Cairo or New Orleans, or the southern tip of Japan, the feedback becomes self-sustaining. The amount of sunlight being reflected at that point is sufficient to cool the remaining open water fast enough that ice can advance faster than any seasonal warming can push it back. Models describe this as a bifurcation point. A word borrowed from mathematics, meaning the moment a system jumps from one stable state to another. Before 30 degrees, the ice can still be stopped. After 30 degrees, it can't. Ice reached 30 degrees latitude. And it didn't slow down. It crept past the low latitudes. Then it sealed the warm currents that had circulated heat from the equator toward the poles. Currents that no longer had anywhere to go, because the poles were already frozen and the equator was freezing. What had been a planet with ice caps became a planet with an ice belt, then an ice shell. The belt was closing. The ice did not stop. Continuous. The equatorial ocean, the last open water on Earth, the warmest latitude, the place where 750 million years' worth of greenhouse balance had kept the seas warm enough for bacterial mats and dissolved chemistry in the slow accumulation of life, froze. Not over a season, not over a century, over thousands of years, perhaps tens of thousands. Ice advanced from both hemispheres toward the middle. At some point it met itself. The circle closed. Earth was white. Layer by layer, the sediment records what happened. Diamictite in the tropics, striations at the equator. Rocks cannot lie about this. Consider the dropstone again. This piece of rock had crossed that frozen ocean, embedded in a glacier that moved over what's now the tropics, scraping and grinding and dropping fragments into the mud below the ice. The dropstone that landed in the seafloor back when the planet froze, that landed in a world that had no open water, no unfrozen coastline, no place where the sun's light could reach the surface of the sea. It landed on the bottom of an ocean that was sealed shut. There's something strange to consider about that rock. The same stone can hold warmth or cold, depending only on what touches it. Earth did something similar. For the long pre-Sturtian eon, it was warm because the air touched it with greenhouse gases. Then the air lost its warmth, and the ice touched everything instead. I try, sometimes, to picture what the planet looked like in full snowball form. It isn't easy. The mind has certain images it reaches for when it hears the word ice, Antarctic landscapes, frozen lakes, the white edge of a Scandinavian winter. None of them are adequate. Local events, all of them. A frozen lake is, after all, just a feature embedded in a living landscape that carries on around it. The Antarctic ice sheet, enormous as it is, sits on one continent at one pole, while the rest of the planet carries on around it. What happened 717 million years ago was different in kind, not just in degree. Every surface was ice, every ocean, every landmass, every latitude from pole to pole. Ice, perhaps a kilometer thick over the equatorial ocean. Exact thickness uncertain, models disagree. Thinner near volcanic hotspots, thicker in the polar basins where it had been gathering the longest. Surface temperature, globally averaged, was somewhere around minus 40 degrees Celsius. No one knows the exact figure. Models give different answers. Locally, perhaps minus 50. The kind of cold that doesn't register as discomfort but as something more absolute. A negation of warmth as a concept. A world in which heat is a local exception rather than a general condition. On the frozen equator, the landscape would have been flat, white, featureless in most directions, the way an ice shelf is featureless, not smooth exactly, because ice fractures and ridges and heaves under its own pressure, but lacking any of the variety that comes from liquid water interacting with rock and air. There would have been wind. Temperature differences between the equator and the poles were smaller than today. Both were frozen, but they weren't equal. The atmosphere still moved, a dry wind, bitterly cold, carrying ice crystals stripped from the surface and depositing them a few hundred meters downwind. What would that wind have sounded like, crossing a frozen ocean? Thin and high, a thin tone ice produces when air moves over it without anything to catch or slow it. No trees to rustle. No waves to break. No loose soil shifting underfoot. Just the wind and the ice and the long white distance. Cold places exist on the modern Earth. Outposts in interior Greenland, where the ice carries to the edge of sight in every direction, and the air is so dry it feels like breathing paper. But even there, the ocean is at most a few hundred kilometers away. There's a coast. Somewhere the ice ends, and the world resumes. In the Sturgeon Snowball, there was no such somewhere. Ice didn't end. It was continuous, a shell wrapping the planet as a rind wraps a fruit. Underneath it, the ocean sat in darkness, cut off from the air, cut off from the sun. Nothing moved. Stillness. Quiet of a snowball, Earth isn't something the geological record preserves directly, but it can be inferred from what's absent. Sedimentary record for this period is noticeably thin. Normally, sediment buildup in the ocean is driven by biological output. Organisms living and dying in the surface waters, their remains drifting to the bottom, and separately by the weathering of continents, which carries dissolved material to the sea through rivers. In the snowball state, both processes nearly stopped. The ocean surface was frozen, so there was no photosynthesis. Continents were buried under ice, so there was no chemical weathering, no rivers delivering minerals to the coast. Sediment that accumulated on the seafloor during the Sturgeon event is thin and dark, and largely without life trace. It's the record of a world in which almost nothing was happening at the surface. Almost nothing. That word is important. Below the ice, the ocean was still liquid. This stands among those facts that seem contradictory until the physics is explained, and even then it retains a quality of quiet wonder. Ice, thick as it was, acted as an insulator. It sealed the ocean from the minus 40 atmosphere above, and the ocean, heated from below by Earth's interior, by geothermal heat flowing through the crust, by the slow radioactive decay of uranium and thorium and potassium in the mantle, stayed liquid. Cold, yes, perhaps minus 2 degrees in places just above the freezing point of seawater, but liquid. And warmer in places where the crust was thinnest, where mid-ocean ridges spread and volcanic vents pushed heated water into the deep. The ocean was warmer still. I find it a comfort, in some way that has nothing to do with the science, that the ocean persisted. Water still moved. Even in the most extreme glaciation the planet has ever known, there were still currents driven by temperature differences between vent-warmed patches and the ice-cooled basins around them. Circulation must have been sluggish, nothing like the great ocean currents that move heat around the modern planet. But it was there, a slow, deep, patient movement of water through absolute darkness, carrying dissolved minerals and heat from one part of the seafloor to another. In that water, near those vents, life continued. Hydrothermal vents were the world's last outposts. Black smokers, chimneys of mineral precipitate rising from the floor of the deep, where heated water, rich in hydrogen sulfide and iron and other dissolved metals, met the cold ocean around them. Today, these vents host entire communities independent of sunlight. Tube worms, shrimp, mats of bacteria that run on sulfur. Through the Sturtian snowball, the communities were simpler, mainly bacterial and archaeal, organisms that drew their energy not from the sun but from chemistry, chemosynthesis, the oxidation of iron or hydrogen sulfide as a source of fuel-driven fuel. These were not, in any sense the word allows, organisms patiently waiting for the ice to melt. They had never needed warmer surface conditions in the first place. They were organisms that had never needed the sun in the first place, built for darkness, pressure, the steady chemical output of Earth's own interior. They continued, unhurried, in the warm plumes rising from the vents, while the surface above them was locked in a quiet that would last for tens of millions of years. Other refugia likely existed as well. Some climate models suggest that thin ice or patches of open water persisted near volcanic islands, places where geothermal heat was high enough to keep the ice from closing completely. Those oases were small, ephemeral, few, perhaps 1,000-odd kilometers of open water with a planet-sized ice sheet around them. But for single-celled organisms capable of photosynthesis, even a small patch of open water with light filtering through thin ice would have been enough. Not abundant, not comfortable, but enough. Life, I've come to believe after a career spent reading rocks, doesn't require comfort. It requires chemistry and liquid water and a source of energy, and it'll find all three in the most improbable settings. The Snowball Earth was, by any measure, the most extreme glaciation this planet has produced for surface life. And life didn't leave. It shrank. Into the margins it went, into the depths and the warm spots near volcanic plumes. But it held on. Under a kilometer of ice, in total darkness, the ocean was still alive. Not thriving, not growing, just persisting, the way life does. By this point in the story, the picture is one of absence. No sunlight on the ocean, no open coastlines, no photosynthesis across most of the world's surface. And yet the life that persisted through the Sturtian glaciation wasn't, in any meaningful sense, diminished. It was different, running on a different engine. And understanding that engine requires thinking about what the Earth provides from below, rather than what the sun provides from above. Hydrothermal vents weren't new features of the Sturtian Ocean. They had been active for billions of years before the ice arrived. Part of the planet's continuous geological machinery, the mid-ocean ridges spreading, the mantle convecting, the crust recycling. What was new, during the snowball, was their relative importance. In a world with an open ocean, hydrothermal vents are footnotes. Interesting, biologically productive in their local neighborhoods, but marginal compared to the vast surface ecosystem powered by the sun. Once the world was sealed under ice, those vents became the center of everything. The footnote became the text. Chemistry is worth lingering on, not because it's naughty, but because it's beautiful in its simplicity. Vents emitted water heated to 300, sometimes 400 degrees Celsius, far above the boiling point at the surface, but kept liquid by the immense pressure of the ocean above. That water carried dissolved minerals from the crust: iron, manganese, zinc, copper. Most importantly, hydrogen sulfide. When the heated vent fluid met the cold ocean around it, the minerals fell out of solution, forming the chimney towers that modern deep-sea craft have photographed in detail. Black, mineral-encrusted towers rising from the seafloor, some of them 20 or 30 meters tall, venting dark clouds of precipitate into the water. Around those chimneys, bacteria thrived. Not sun-dependent bacteria, no light reached them to use, but chemistry-fed life that drew energy from the chemical gradient between the hot, sulfide-rich vent fluid and the cold, oxidized ocean water. The reaction is similar to what a battery does. Energy released by the movement of electrons from one compound to another. In this case, the bacteria oxidized hydrogen sulfide, using that energy to build organic molecules, their cells, without a single photon of sunlight. I have read the papers on chemosynthetic metabolism many times, and what never ceases to impress me isn't the complexity of the chemistry. It's reasonably straightforward, as biochemistry goes, but the independence of it. These organisms needed nothing from the sky, nothing from the air, and nothing from the surface world at all. Fed by the Earth itself, their energy came from Earth's interior, from the same heat that drives plate tectonics and builds mountains and opens ocean basins, in the most literal sense. Had the sun gone out entirely, these organisms could have continued. That isn't a metaphor. It is a factual statement about the biochemistry. Accounts differ on how widespread these refuges actually were. Estimates range by a wide margin. Nobody knows the true extent of the deep ocean living world during the Sturtian. Warmth they needed came from below. Chemicals they needed came from below. Liquid water they needed was maintained by pressure and geothermal heat. Everything pointed downward, toward the core, away from the frozen surface, and the weak, distant star that could no longer warm it. That life can persist independently of the sun is one I've met many times across the literature, and it has never stopped feeling like a quiet revelation. It changes the way the question of habitability gets framed. Habitability turns out not to be a surface condition, but a geological one. A planet with a hot interior and liquid water and the right dissolved chemistry can carry life even if its surface is frozen solid, even if its star is too faint or too far away to matter. There is a term in space biology for this: undersurface refuge. It's why scientists are interested in Europa, Jupiter's ice-covered moon, where a liquid ocean lies beneath perhaps 15 kilometers of ice, warmed by tidal heating from Jupiter's gravity. Had the Sturtian snowball been permanent, had the ice never melted, the life beneath it could have continued with no end, as long as Earth's interior kept providing heat and chemistry. The planet might have resembled Europa, a frozen shell over a dark, living ocean. But the snowball was not permanent. That's a story for later. For now, what matters is what survived, and how, and what that survival tells us about the nature of life itself. Not all the survivors gathered around hydrothermal vents. The deep ocean, even away from the ridges, wasn't uniformly hostile. Dissolved organic matter, remnants of the pre-glacial biosphere, dead cells and metabolic residues that had drifted through the water column before the ice closed the surface, provided a thin but persistent food source for scavenger bacteria. Organisms that could metabolize these dissolved scraps, slowly, in the cold and dark, would have persisted throughout the deep ocean, not concentrated at any single point, but distributed thinly, doing what bacteria do best: enduring. Then there were the volcanic oases, climate models developed by researchers at Harvard and Caltech and the Australian National University, among others, suggest that volcanic hotspots and island arcs could have maintained patches of open water or very thin ice, allowing small amounts of sunlight to penetrate. These patches would have been rare and widely separated, perhaps a few thousand square kilometers in total, across a planet with over 500 million square kilometers of surface. small, scattered, ephemeral, lasting decades or centuries before shifting volcanic activity or ice dynamics closed them, but sufficient in each generation for a small population of sun-dependent life to persist. I think about those organisms more than is probably productive. Single-celled, photosynthetic, holding to a patch of thin ice near a volcanic island, drawing just enough light to fix carbon and reproduce, while the rest of the planet lay buried under a kilometer of frozen water. They weren't heroic, nor striving. They were doing the only thing single-celled organisms do, which is to continue existing as long as the chemistry permits. But the fact that they continued, that some populations of sun feeders made it through that frozen eon, passing their inheritance from one generation to the next in tiny, precarious patches of marginally habitable water, is, to me, one of the quieter wonders in the history of the planet. Consider the dropstone again. This rock had traveled across that frozen world, carried by ice that covered the warmest latitudes on Earth. And beneath that ice, life had been going about its business in the black. Bacteria around the vents had not known the ice was there. Photosynthesizers in the volcanic oases hadn't known the ice would ever leave. Both had simply continued in their different ways, with their different metabolisms, running on whatever chemistry the planet provided. Somewhere overhead, there may be other planets with frozen surfaces and liquid oceans beneath. Hydrothermal vents on those worlds, too. Chemosynthetic bacteria around those vents, drawing energy from the chemistry of their own planetary interiors, knowing nothing of the sun or the stars. That thought sits quietly. Some thoughts are better left alone in total darkness, gently called, without trying to turn them into anything more than what they are. 58 million years. That's how long the Sturtian glaciation lasted. The number arrives in papers, in lectures, and it never quite becomes a number the mind can hold. It does not resolve into a duration as a year resolves, or a decade, or even a century. The number arrives flat. How does a human mind hold a duration like this? It was built for seasons, for the rhythm of planting and harvest, for the span of a life and the memory of a grandparent's stories. Even the largest human civilizations, the ones that feel ancient when we read about them, Egypt and Mesopotamia and the Indus Valley, occupy perhaps 5,000 years, 100 generations. Sturtian ice lasted roughly 11,600 times longer than the entire human story. Ice sat on the planet like a stone at the bottom of a river, and neither the stone nor the ice was in any hurry to move. 58 million years, the whole age of mammals would fit inside the Sturtian with 20 million years to spare. Everything that has happened after the Yucatan asteroid ended the Cretaceous, the rise of grasses, the spread of forests, the evolution of whales from small land mammals and horses from animals the size of dogs, the ice ages of the Pleistocene, the emergence of hominids, and the slow, patient development of a species capable of asking what an ice-covered world looked like. All of that fits within the Sturtian. The Sturtian still has room left over. Room enough for another 20 million year stretch of ice, sitting there, doing nothing in particular, while the planet turned beneath it. This is difficult to convey because the difficulty is the point. Sturtian wasn't an event in the way a volcanic eruption is, or an asteroid impact, or a flood. Those things happen. They have a beginning, a middle, an end. Sturtian simply persisted. Ice formed. The planet went white. Then, for a span of time so long that the word patience loses all meaning, the ice stayed. Sun rose and set. Earth orbited and orbited again. What does a planet do for that long with nothing to mark the time? Stars in the sky drifted slowly against each other. Because that long an interval is enough for the constellations to rearrange themselves, for stars to be born and die, for the Milky Way itself to rotate a perceptible fraction of its great wheel. On the surface, nothing changed. Wind blew across the ice. Crystals formed and were stripped away and deposited elsewhere, and then those were stripped away in turn. Glaciers advanced where gravity pulled them and stopped where geometry held them, and the cycles of pressure and fracture and refreezing went on in total darkness, the way tides go on, whether or not anyone is watching. On the frozen equator during the 10th million year of the Sturtian, the planet would have looked exactly as it had during the first million year, and exactly as it would during the 50th. The only clock that mattered was the geological one, and it was running so slowly that its movement was almost the same as stillness. Desert air at night has a quality that suits thinking about durations like this. Stars don't twinkle the way they do in humid climates. Air is dry and still, and the light from the stars arrives clean, without the shimmer that comes from passing through turbulent atmosphere. Distance between the stars and the ground feels shortened in that kind of air, as though the atmosphere has simply gotten out of the way. And the stars themselves aren't moving, or rather, they're moving at a rate too slow to be detected, which is the same thing as stillness. The Sturtian was like that. Movement so slow it felt like permanence. Change so gradual, it was indistinguishable from absence. Warmth fades slowly from desert stone at night. The loss happens degree by degree, a slow release that mirrors in miniature what happened to the planet. Warmth leaving, degree by degree, replaced by something colder and more patient. During all those ages, the planet wasn't entirely still. Geology continued. Tectonic plates drifted beneath the ice. They carried their frozen cargo as a moving belt carries boxes through a warehouse, oblivious to the contents. Mid-ocean ridges spread. Subduction zones consumed old crust and sent it back down into the mantle. Volcanic eruptions occurred not on the surface, where ice was too thick for most eruptions to break through, but beneath it, on the seafloor, at the margins of spreading ridges. Occasionally through thinner patches of ice near volcanic hotspots. This is where the Sturtian narrative begins to change. Though that change happened so gradually it would have been invisible for the first 10 million years, the second 10 million years, and perhaps even the third. Volcanoes released carbon dioxide. I keep coming back to that simple fact. They had always released carbon dioxide. It ranks among the fundamental outputs of the mantle's chemical engine, dissolved in magma and freed when that magma reaches lower pressures near the surface. Before the glaciation, this volcanic carbon dioxide had been balanced by the weathering of silicate rock, the slow chemical reaction that consumed it through the dissolution of minerals in rainwater. But the weathering had stopped. Continents were buried under ice. Nobody knows how deep the cover was at any one place. No rain fell on exposed rock, because no exposed rock remained. The thermostat described earlier, the one that had kept Earth's temperature within a habitable range for billions of years, was broken. One side of the equation had been shut off, and the other continued to run. Had the ice not sealed the continents, the carbon dioxide released by volcanoes would have been absorbed by weathering. The atmosphere would have remained roughly in balance. But the continents were sealed. Carbon dioxide had nowhere to go. So it accumulated, molecule by molecule, eruption by eruption, century by century, in an air mass that was otherwise frozen and still. Greenhouse was rebuilding itself, not because anyone or anything intended it, but because Earth's interior kept doing what it had always done, releasing gas, while the surface had lost the ability to respond. I think of it as a slow leak, a very slow leak. Carbon dioxide leaking into an atmosphere that can't absorb it, building up like mud at the bottom of a still pool, layer upon invisible layer, so gradually that no instrument of the time, had any existed, could have measured the change from one millennium to the next. Concentrations rose. No one would have noticed. The warming effect was tiny at first, far too small to melt ice that was a kilometer thick at the equator, and surrounded by an air mass averaging minus 40 degrees. But the carbon dioxide was accumulating. Year after year, million after million, the greenhouse was thickening. Ice remained, albedo held in full force. Every photon of sunlight that reached the white surface bounced back into space, carrying its energy away from the planet. Faint sun, still 6% weaker than it would eventually become, shone on a world that bounced back nearly all of its light. Yet beneath that brilliant, unyielding white, the air was slowly, quietly below notice, filling with the gas that would eventually bring the ice to an end. The paradox of the Sturtian is that the longer the ice lasted, the more certain its eventual end became. Every year of ice was a year without weathering. Every year without weathering was a year of unchecked volcanic outgassing. And every year of unchecked outgassing was a year the greenhouse thickened. The ice was building the conditions for its own undoing, as a dam builds pressure against the water it holds back. Not quickly, and not in any way that could be noticed, but with the steady, patient accumulation that characterizes everything the Earth does when left alone with its own chemistry. Above the ridge tonight, stars turn at a rate the eye cannot see. Were the night long enough, you would notice. If anyone had stood on that ridge through the long ages, they would have seen the constellations themselves rearrange. Somewhere in the rock beneath sits the record of an interval that long, compressed into stone. The ice had been patient, but the volcano was more patient still. The thaw didn't arrive as a spring arrives, with the gradual warming of soil and the first green shoots pushing through softened ground. There was nothing gradual about what happened to the Snowball Earth when the greenhouse finally reached its tipping point, though the word finally covers an almost absurd span of time. Carbon dioxide had been building across long ages, released by volcanic eruptions into an atmosphere sealed under ice, accumulating in concentrations that have no parallel in the modern world or in most of the geological record. How much CO2 was needed to break the freeze? Accounts differ between research groups, and I've read enough of the competing papers to know that nobody knows the precise number. But the general consensus is that carbon dioxide concentration in the atmosphere needed to reach about 350 times the modern level before the greenhouse effect could overpower the Ice-Albedo feedback that had kept the planet frozen. 350 times. Today's atmosphere contains roughly 420 parts per million of carbon dioxide. The Sturtian endgame required something close to 150,000 parts per million, a level so high that the air itself felt different, thicker in a chemical sense, though not in a way that would have been visible. Had anyone been present to breathe that air, it would have tasted faintly sour. Carbon dioxide in high concentrations produces a mild carbonic acid reaction on moist surfaces. The tongue, the lining of the nose, the membranes of the eyes. It isn't dangerous at the levels that ended the snowball. Not at once, but it would have been palpable. An air that felt different from the modern air over these same ancient ridges, though the ridges themselves had once sat beneath exactly that sky. Warming, when it came, was not symmetrical. It began where ice was thinnest at the equator, where sunlight was strongest and the ice had always been under the most thermal stress, and near volcanic hotspots where geothermal heat added to the greenhouse warming from above. Cracks at first would have been small, melt pools forming on the surface of the ice, absorbing sunlight instead of reflecting it, warming the ice around them, widening. A patch of dark water appearing where there had been only white, a hole in the planet's white shell, no larger perhaps than a small lake. That small patch of dark water changed the equation. It absorbed heat instead of reflecting it. The direction had flipped. The surrounding ice warmed, which melted, which created more dark water, which absorbed more heat. The Ice-Albedo feedback that had frozen the planet was now running in reverse, and it was running with the same relentless logic it had always possessed, except that the direction had changed. Instead of ice making more ice, open water was making more open water. And the pace of that reversal, once it crossed the critical threshold, was extraordinary by geological standards. If you trust the models, and most geologists do, they suggest that the final collapse of the ice sheet, from the first significant melt to the last major glaciers, may have taken as little as a few thousand years, perhaps as few as 2,000. A geological instant. After ages of ice, the thaw compressed into that instant. A length of time so short relative to what came before that the geological record marks it as a boundary, a line between one rock type and another, as sharp as a knife drawn through mud. That boundary is one of the most easy to spot features in Neoproterozoic stratigraphy. It's called a cap carbonate. Cap carbonate tells the rest of the story. It's a layer of carbonate rock, limestone or dolostone, usually pale, sometimes pink or cream-colored, that sits directly on top of the glacial diamictite. The transition is immediate. 1 centimeter, the rock is full of glacial debris, dropstones till, the jumbled sediment of an ice sheet grinding across a continental shelf. The next centimeter, the rock is clean carbonate, chemically precipitated from warm seawater, saturated with calcium, and dissolved carbon dioxide. There's no gradual transition. No mixed zone where glacial sediment and carbonate interleave. Ice ends and the warmth begins, and the rock records both with the bluntness of a ledger entry. A piece of cap carbonate at this kind of outcrop is smooth and surprisingly warm in the dusk light. Not from the geology, but from the afternoon sun that has been warming it all day. Texture is fine-grained, almost waxy. The kind of carbonate that precipitates quickly from rich water. It feels different from the rough diamictite beneath it. Softer, lighter. Product of a world that had been cold for so long that when the warmth finally returned, the ocean couldn't hold all the dissolved minerals it had gathered. They fell out of solution like snow falling from an overloaded cloud, coating the seafloor in a blanket of fresh carbonate. An immediate transition like that calls for explanation. The chemistry is elegant, in the way that geological chemistry often is when viewed from a sufficient distance. Across those long ages of ice, the ocean had gathered dissolved calcium and bicarbonate from hydrothermal vents, and from the steady input of volcanic gases into seawater. With the ice covering the surface, no photosynthesis was left to consume the carbon dioxide. No life-driven pump to draw carbon into the deep. No weathering to deliver fresh material from the continents. Ocean chemistry had drifted far from equilibrium, loaded with dissolved minerals that had nowhere to go and nothing to react with. When the ice melted and the warm, carbon dioxide-rich atmosphere met the mineral-laden ocean, the result was a massive, rapid precipitation of carbonate. Cap dolostone formed in what geologists will call a blink, perhaps a few tens of thousands of years, across virtually every continental shelf on Earth at once. I find it reassuring, in a quiet way, that the evidence is so clear. Diamictite says, ice was here. Cap carbonate says, and then the ice left and the world was warm. The ocean released what it had carried. 2 rocks lie together in outcrops across Namibia, Australia, northern China, Svalbard, and other distant ridges. The same sequence, the same transition, on every continent. A planet that froze and then thawed, recorded in stone that anyone with a hammer and a hand lens can read. What emerged from the Sturtian wasn't the world that had entered it. The atmosphere was thick with carbon dioxide, warmer than it had stood in deep time. Oceans were warm and rich with dissolved iron and other metals that had accumulated during the long darkness. Continents, freed from their ice, were raw and bare. Exposed rock? No soil, no vegetation, nothing growing in the open surface. Rainfall, when it came, fell on that bare rock with the same chemical appetite it had shown during the weathering that triggered the freeze in the first place. Silicate weathering thermostat began to operate again, slowly drawing down the excess carbon dioxide, slowly cooling the planet back toward a more moderate state. Recovery took ages. Were the planet to refreeze tomorrow, it would take just as long to thaw. Nothing in this story is fast. The exact pace remains unclear, and accounts differ from one outcrop to another. Nobody knows the full answer. But the trajectory was clear, and the outcome was a planet with open oceans, a functioning carbon cycle, an atmosphere settling slowly toward a new equilibrium, one that would hold more or less for the next 70 million years. Two pieces of the same story sit in different places now. Dropstone embedded in the Namibian ridge. Cap carbonate stored in collections, pale, smooth, fine-grained. One the record of ice that covered everything, the other the record of its departure. The planet had thawed, ice had retreated, the oceans had warmed. Carbon cycle had found something resembling balance again. And for roughly 70 million years, Earth held a kind of healing quiet, not fully recovered. Not quite the world it had been before the Sturtian, but functional, liquid, alive in its waters and across its bare, weathering continents. In time, the ice gathered again. This will matter later. I've told this part of the story to students and to colleagues, and the response is often a kind of quiet disbelief, a pause, a stillness, a sense that the mind needs a moment to accept it. Underlying reason isn't difficult once the mechanics are clear. The conditions that had caused the first freeze hadn't been permanently resolved. The planet had warmed because the volcanoes had rebuilt the greenhouse while the ice prevented weathering from consuming it. But the underlying geometry was still wrong. Continental fragments that had drifted apart at Rodinia's breakup were still positioned in the tropics, exposing fresh silicate rock to warm, wet weather, drinking carbon dioxide through the same grain-by-grain chemical process that had thinned the greenhouse the first time. Details of the second glaciation, the Merino Wen, which began about 650 million years back, are similar enough to the Sturtian, but there's no need to walk through every mechanism again. Greenhouse thinned. Ice advanced from the poles. Albedo feedback locked the planet into a frozen state once it crossed the critical latitude. The world went white. Oceans were sealed. Life retreated to the same dark refugia it had occupied before. The hydrothermal vents, the volcanic oases, the cold deep water where heterotrophic bacteria continued their slow metabolism of dissolved organic remnants. Merinoan was shorter, 15 million years roughly, compared to the Sturtian's 58. Not less extreme. The geological evidence suggests that ice was just as thick, temperatures just as cold, the coverage just as global. But it lasted a fraction of the time. Volcanic activity may have been stronger during this period, or perhaps the configuration of continents had shifted enough to alter the balance between carbon dioxide output and weathering consumption. The precise reason is still debated, and I've read the competing hypotheses without forming a strong preference. What matters for the purposes of this story is that the planet froze again. Then it thawed again. Evidence for both events is written in the same rocks, in the same outcrops, divided by the between-ice mud of those 70 million years of recovery. In the Namibian outcrop, a second dropstone rests in the rock about 3 meters above the first. It is smaller, roughly walnut-sized, and rounder, polished by glacial transport, in a manner that hints, though one can't say with certainty, a longer journey or a softer parent rock. First dropstone comes from the Sturtian diamictite, 717 million years old. Second comes from the Merino Wen diamictite, 650 million years old. They're separated in time by roughly 67 million years, and in the outcrop by 3 meters of rock, the compressed record of a warm period in which the planet had warmed, then cooled, then frozen again. 2 glacial erratics, 2 fragments of rock carried by ice across a frozen ocean and dropped into the mud of a sealed seafloor, separated by an unimaginable interval of planetary history. Sturgeon dropstone, heavier, rougher. Merino and dropstone, smoother, lighter. Despite the gulf of time between their origins, the two stones look by a striking margin alike. The same rough texture of glacial transport, density alike, mineral coolness alike. Without their stratigraphic positions known, the two stones couldn't be told apart by touch alone. Sturgeon rock and Merino rock feel like one event, which in a way they were. One planet, running the same chemistry, arriving at the same frozen conclusion by the same mechanism, divided only by time and by the slow, recurring patience of a carbon cycle that couldn't quite keep its balance. Sturgeon dropstone has a small inclusion on one side, a darker mineral grain, probably pyroxene, embedded in the lighter matrix. Merino dropstone is more uniform, a fine-grained gray wacky, a rock that forms from the weathered fragments of older continental crust. Both had traveled in ice. Both fell through cold water. They landed on the bottom of an ocean that had no business being frozen, and both waited in the quiet dark of the sediment for the eon that followed. Two frozen worlds, separated by an unimaginable interval, both small enough to rest in a cupped hand. 40 kilometers to the west, the Atlantic continues doing what it has been doing since the ice retreated for the last time. Moving water, carrying heat, circulating the dissolved memory of every chemical reaction that has ever taken place in its basin. Liquid water, a world that thawed and stayed thawed, warmth returning and persisting and carrying the whole improbable enterprise of complex life forward into whatever came next. What the ice left behind, written in the diamictite and the cap carbonate in the two small stones resting in the Namibian ridge, turns out to be the most consequential thing the planet ever did. What the ice left behind wasn't what came before it. Merino and ice retreated. The greenhouse recovered. The oceans warmed. The cap carbonates formed their smooth, pale layer across the seafloor. And something happened that had never happened before in 4 billion years of planetary history. Complex life appeared, not bacteria, not the single-celled organisms that had persisted in the dark, at the vents, in the thin film of liquid water between the ice and the rock. Something else, a class of organism that left imprints in the rock of southern Australia, in the shales of Newfoundland, in the layered beds of Namibia, the same country whose ridges still hold the dropstones of the freezing. Ediacaran biota, as they're called, rank among the strangest organisms in the fossil record. Their imprints appear in collections and field exposures on many continents. Ediacaran rock from the Flinders Ranges, layered beds at Mistaken Point. And what those imprints reveal is the faint raised outline of something that looks like nothing else in geology. Not a shell, not a bone, not a bacterial mat or a stromatolite, or any of the familiar forms the Proterozoic had been producing for the 2 billion years prior. Soft-bodied, recorded as casts and molds in fine-grained mud, their forms were alien. That is the right word. Dickinsonia, the most recognizable, looks like a flattened oval with radiating ridges, as though someone had pressed a quilted pillow into wet sand and removed it carefully. Charnia resembles a frond, branching in a fractal pattern that repeats at every scale. Kimberella has been compared to a mollusk, though the match is generous, because whatever Kimberella was, it was something the planet had not tried before. A Dickinsonia imprint, kept in sandstone, shows raised edges roughly 1 millimeter high, with grooves between them filled by the fine silt that settled around the body after death. Organism itself was soft, would have felt something like a firm leaf or a thick piece of wet fabric while it was alive. What the cast preserves is the negative space where the body once was, the absence of the creature, preserved in rock, as a footprint preserves the absence of a foot. These organisms appeared in the fossil record within a few million years of the Merino and Ice's retreat. Timing is not coincidental, and the geologists who study the Ediacaran period have spent decades working to understand the connection. Leading view is that the snowball glaciations did something to the ocean chemistry that made complex layered life possible for the first time. Ice had sealed the oceans and reduced the oxygen available at the surface. But not the depths. Beneath the ice, the hydrothermal vents continued to release minerals, including phosphorus and iron, which accumulated in the deep ocean water across the deep ages without being consumed by photosynthetic organisms. When the ice melted and the oceans mixed, those accumulated feedstocks flooded the shallow waters, triggering an expansion of sun-driven activity. Cyanobacteria, algae, the organisms that take in carbon dioxide and release oxygen. Oxygen levels in the air, and the shallow ocean rose, perhaps to their highest point in a billion years. With more oxygen came the metabolic option of larger, more complex organisms. Cells that needed more energy could get it. Bodies that required oxygen diffusion through multiple tissue layers could endure. Ice had, in effect, fertilized the planet. It had locked up the nutrients in the deep ocean, held them away across vast ages, and then released them all at once in a post-glacial bloom that changed the direction of life on Earth. It's the kind of thought that takes a while to settle. Two frozen worlds. Between them and the present stretches the entire history of complex life. Everything that came after. Cambrian explosion, the fish, the forests, the dinosaurs, the mammals, traces back through a chain of oxygen and nutrients and evolutionary chance to the aftermath of the ice. The ice didn't come to destroy life. It came to change it. That sentence came at the start of the story as a reframing, a way of turning the story before it had been told. By the end, with the dropstones still in the rock and the fossil impressions vivid in the record, the sentence has a different weight. It sounds less like a reframing and more like the truth, waiting for the evidence to catch up with it. Life had changed. Not through slow accumulation across stable eons, but through a long stillness and a chemical opening that followed. Ediacaran organisms were the first to move through that opening, taking forms so gentle and strange that even now, across the long ages since, the question of what they were hasn't been settled. Whether they were animals or something else, or something in between, a category that the planet tried once and then quietly set aside when the Cambrian arrived with its harder bodies and its own patient ways. I don't know. The fossil record doesn't resolve the question, and I've read enough conflicting papers to know that it won't resolve it soon. What's certain is that the organisms preserved in the Ediacaran sandstone were the first visible expression of a complexity the planet had been building toward 4 billion years. That they appeared not in spite of the ice, but because of it. No one can yet say how the chemistry turned, only that it did. Glaciation was not an interruption of life's story. It was a chapter. Perhaps the most important chapter. And the dropstones in the rock, warm in the lingering heat of an old afternoon, are the period at the end of the cold sentence and the first letter of the sentence that followed. Night is fully settled. The kind of dark that desert places reach when there's no moon and no light pollution, when the only illumination comes from the stars and from whatever ambient glow the air itself carries at high altitude. Ridge has lost most of its afternoon warmth. Rocks of the desert return their stored energy to the clear sky the way all rock does at night, slowly, without resistance, a process as old as the planet itself. Ice comes to mind. Not the Sturtian or the Merinoid in particular, but ice is a thing the Earth does, the way it does volcanism or plate tectonics, or the slow cycling of carbon through rock and air and ocean. Ice isn't an anomaly in Earth's history. It's a recurring visitor, arriving when the conditions permit, staying for as long as the chemistry holds. then retreating, eventually returning, following a rhythm that's partly driven by orbital paths and partly by the arrangement of the continents and partly by the composition of the air and partly by the slow brightening of a sun that has been growing steadily warmer. Across 4.5 billion years, cryogenian ice was the most extreme version of this tendency, but it wasn't the only one. The reason one ice age extends beyond another isn't fully understood. There were glaciations in the late Ordovician, around 440 million years back, when ice spread across a southern supercontinent called Gondwana, and the tropical seas cooled enough to quiet the reefs. Other glaciations followed in the late Paleozoic 300 million years back, when the coal forests of Pangaea drew down carbon dioxide and the planet rested in cold for 60 million years. And there's the current ice age, the one that began roughly 34 million years ago when Antarctica drifted over the South Pole and the polar currents sealed it in cold water. The Ice Age, whose glacial interglacial cycles carved the fjords and the lake valleys and the river valleys that hold the cities where most of the world now lives. Ice is patient. It comes when the chemistry invites it, and it doesn't leave until the chemistry changes again. While it's here, it reshapes the surface of the world with a thoroughness that no other geological process can match. Glaciers carve valleys. Ice sheets push the crust down under their weight, pressing the land into the mantle like a heavy book on a mattress. And when the ice retreats, the land rises back slowly, over thousands of years. A process called slow rebound that's still happening today in Scandinavia and northern lands, where the ground is lifting at a rate of about a centimeter per year because the last glaciers melted only 12,000 years ago, and the Earth has not yet finished recovering. Dropstones, two small pieces of a patient process, were carried by ice that had no intention and no awareness and no schedule, except the one imposed by the physics of a planet orbiting a star. Ice had come and gone and come again, and after it left the second time, the world was different in a way that mattered more than anything the ice itself had done. Reshaping was not the point. The point was what grew in the space the ice had cleared. Stars above a Namibian ridge tonight aren't the same stars that were overhead when the ice first formed. If anyone had sat here through that interval, they would have seen entirely different patterns. 700 million years stretches long enough for the constellations to rearrange entirely, for stars to be born and age and settle, for the Milky Way to rotate nearly 3 full turns on its axis. Light visible now is old, some of it thousands of years old. But the patterns it makes are new, arrangements that'll look different a million years from now, and different again a million years after that. Sky is not fixed, nothing is fixed. Ice comes and goes, the stars rearrange, continents drift and collide and break apart. Only constant is the change itself, slow and patient and indifferent to whether anyone is watching. Air over the ridge is still. Somewhere out in the dark, the Atlantic continues doing what it has been doing since the ice retreated for the last time. Moving water, carrying heat, circulating the dissolved memory of every chemical reaction that has ever taken place in its basin. Ocean does not forget. It holds its history in the ratios of its isotopes and the concentrations of its dissolved minerals. The way the ridge holds its history in the layers of diamictite and cap carbonate and sandstone. The ridge is quiet. Wind hasn't returned, and the air holds the particular stillness that comes after a desert has released its last heat, when the temperature at ground level and the temperature just above are so nearly equal that the atmosphere has no reason to move. Rocks of the ridge, still faintly warm in their depths from the long afternoon, cooler at the edges where the stone meets the open air, sit as they have sat across the deep past. Dropstones embedded in them are part of the rock now, 2 small, dense fragments of a thought the planet's been carrying for an unimaginable interval. The weight of 2 frozen worlds settled against the side of a continent. Stars are overhead, not arranged in any pattern with a familiar name, not doing anything except being there. The way the rocks are being there, the way the ocean is being there, 40 kilometers to the west, moving in the dark, without anyone watching it move. Light from the nearest of them has traveled for a few years to reach this ridge. Photons from the farthest have traveled for longer than the ice had lasted. Consider the sandstone slabs in Australia, the imprints of Dickinsonia pressed into the rock like the memory of something soft that had once rested there, and then was gone. Consider the cap carbonates, pale and smooth, the warm handshake that ended a cold epoch. Recall the hydrothermal vents in the dark-sealed ocean, the organisms that had persisted without sunlight across the long ages. Running on the heat of the planet itself, waiting for nothing because waiting implies expectation. And these were organisms that simply continued. The rocks have been heard. Full account lives in the diamictite, and the cap carbonate and the two little rocks still resting in the Namibian ridge. It lives in the layered beds of the Flinders Ranges, where the first complex life left its print. It's in the isotope ratios of 700-million-year-old marine carbonates. The story has been read in stone all evening. And now the rocks are warm, and the sky is dark, and the ridge holds the layers as it has held them for all of this time. Patiently, without comment, as rock holds everything that's laid upon it. Warmth of the stone and the weight of the dropstones and the slow turning of the stars carry the rest of the thought. The one about what the ice meant and what it left, and how the cold and the dark and those distant ages of quiet were not the end of anything, but the long, quiet beginning of something else. That brings us to the end of tonight's story, but only this one. The planet has many more chapters like this, and I'll keep telling them as long as the rocks have something to say. If you'd like to come back for the next one, subscribe. There's plenty more. Thank you for listening tonight. Rest well.